Okay, good afternoon, ladies and gentlemen. Let us start this plenary event 10, Space Education through Nano Pico Satellites. My name is Shinichi Nakasuka, a professor of the University of Tokyo, Japan, and organizer of this plenary event. As you know, in more and more countries, Nano and Pico satellite activities are pursued. These activities started in the 1980s with the primary objective of space education. But recently, it became more than that, more than just education, with practical applications such as remote sensing, space sciences, and so on. Today, in this panel discussion, we'd like to focus on educational aspect of Nano and Pico satellites. Okay, so I'm very happy to introduce the moderator of this panel discussion, Ms. Rei Kawashima, who is the Secretary General of the Japanese Space Engineering Consortium named UNISEC. So, please, Rei.
Thank you for kind introduction. I'm really pleased to be honored to be here as a moderator today. And so let me start. So we are very lucky to have such a good and wonderful panelists today. I will introduce later on, so I'm going to quickly. And here is a goal of the session. What we want to do, what we want to create after this session. The first goal is understand status quo of university nano-satellite projects, which are spreading rapidly all over the world, as you might know. And the second one is share the problems, difficulties, and risks that will influence the nano-satellite activities at universities and discuss the possible solution. The third one is think the role of international collaboration or cooperation for space education through Pico nano-satellites. And I would like to invite all of you to participate in this session. So let's enjoy a participative, interactive panel discussion. Here's session format. Let me explain. First, each of speakers, panelists, will share the overview of university nanosatellite projects in their countries. And then we'll get the comments from a pioneer of university satellite projects. Sir Martin Sweding is volunteering to participate in this session. Thank you very much. And then we will discuss key questions. I will show later on. And in the discussion session, we'd like to share the inputs from panelists and voting from audience. And we'd like to know what you think. And so please participate, please cooperate. Then hopefully we'd like to have Q&A session later on. Okay. So let me briefly introduce nanosatellite and Pico satellite. Nanosatellite is the less than 20 kilogram satellite, and Pico satellite is the less than 1 kilogram. It is the definition of Würzburg University, but it is quite good. So we'd like to use it today. Thank you very much for providing the beautiful slides. And this is also shows how fast, how rapid the amount of launch Pico satellites increase. The number is increasing very rapidly, and then geographically spreading too. Okay, so let me introduce the first speaker, Professor Jordi Puig-Suari. Unfortunately, he was not able to come here, but he kindly made a video speech, so we would like to watch it. And then Mr. Laurent, yes, Mr. Laurent, he's...
Thank you for having me.
Just listen.
Thank you to everybody in the IAC, and thank you to Ray and Dr. Nakasuka for giving me the opportunity to be on this panel. And thank you for accommodating me, even though I cannot be there with you at this time. But through the wonders of technology, we'll see how things work. And you have Roland Coelho, who's one of our key members in our CubeSat team, and he's been launching satellites for a long time. So if you have any questions, he's a great resource. But let me talk about university satellites in the US. There is two main programs at this point in the US. There's the University NanoSat program, which is sponsored by the Air Force, and CubeSats. Both started about the same time, around 1999, but they're very different concepts. University Satellite is a sponsored competition where 10 universities, when one of the universities is selected for flight. However, even though universities have been selected for flight, only a few nanosats from universities have flown due to the difficulty in finding a launch opportunity. This program so far has involved approximately 25 universities, so it's a very successful program. CubeSat, as you all know, is a standard that was created with Bob Twiggs at Stanford and Cal Poly in '99 as well. It's a much lower cost alternative, small 10 centimeter, 1 kilogram satellites designed specifically for universities. We've had more launches because of the low cost and low size. Approximately 47 CubeSats have been launched to date. 35 or so are in orbit. About 50% of the satellites launched were from the US. Not all universities, some industry as well. One of the biggest contributions from the CubeSat program was the ability for new players to jump and start developing satellites. In the US, many universities that were not thinking about building satellites, that had never built a satellite before, decided to join the student satellite world through CubeSat, and that has been a great success for the program. We launched Colombia's first satellite, so new countries are coming in and joining the CubeSat world and trying to get into the student satellite program. We have shown the ability for these small satellites to perform useful missions, and that has evolved into what you could call a professional small satellite community, developing satellites of similar size. On CubeSat, the National Reconnaissance Office, the Army, the National Science Foundation are viewing these satellites as potentially providing useful platforms for missions. So that's a great impact. We've actually gone from student satellites as a proof of concept to real missions with government agencies and industry being involved in trying to use these satellites more effectively. The other big contribution of student satellites, of course, is the student skill set. We're developing very important skills on the students that translate not just to aerospace, but also to other industries. The students learn how to work on complex systems, develop a product from design to integration and testing and operations, and that's useful not just in aerospace, but in many other industries. And thank everybody for listening and for giving me this opportunity to talk to you all. And please, if you have any questions, ask our team there in South Korea, and enjoy the rest of the conference. Thank you so much.
Okay, thank you very much. So next speaker is Dr. Tetsuo Yasaka. He's a Professor Emeritus, Department of Aeronautics and Astronautics, Kyushu University, retired, Japan.
Well, thank you, Ray-san. Well, actually, I'm not really pursuing real projects right now. Perhaps for the person of my age, maybe it's difficult for you to guess my age. My role is to introduce you how these kind of activities started, and I'd like to state something about historical background. In Japan, Japan is a country which had the initiation of space program rather early, especially, well, in Asia at least. However, as far as the university activities are concerned, we are very, very behind at a certain time. And as you see in this chart, in 1993, annual satellite design contest, we started this event so that the university have chances to think and have the students work on real project-like things. We try to have the universities participate through the design work and compete each other. This was inspired by Koreans. Korean had the first its small satellite in 1992, I think. And so, listening to that, oh well, what are we doing? And that was the beginning. And so, the satellite design contest, I think, was very successful in having universities start the real activities. As you can see, these are some of the products of these contests. Now, this stayed only in the design phase only. And actual implementation to hardware started from 1998 University Space Systems Symposium. This is jointly held with the United States and Japan, each year meeting in the beautiful island of Hawaii and having the students sitting and discussing in small dark rooms. And what was proposed in that USSS is CubeSat. Probably all of you know this was proposed in 1998 by Professor Twiggs of Stanford University. And then next year, 1999, he went into CubeSat. I was there as one of the co-chair. I was co-chairing the Japanese side, US side, Paul Coleman of USRA at that time. Well, I'm used to big satellite, big programs, and I thought, wow, a satellite of 1 kilogram? But after listening to him for 30 minutes, oh, that could be beautiful. And this is it. This is the start. And, okay, in Japan we had established UNISEC, and 2003 we had first launches of CubeSat. Oh, that's it? That it? Huh? Yeah, somewhere. Oh yeah, okay. Just quick. Here are the name of the satellite developed and launched in Japan. And, well, this blue one is a sounding rocket, but all others are satellites, and we are expecting some more next year. And so you can see how rapidly these small satellites are being established and launched. And I'm sure this is the similar in other countries too. So this is my, thank you.
Thank you very much. And next speaker is Professor Klaus Schilling. He's a professor and chair for robotics and telematics in the computer science department of the University of Würzburg, Germany. So please.
Yeah, thank you very much. So my task is to give a short survey about activities in Germany. And actually, we started in 2005. I was affected by the virus from Bob Twiggs related to CubeSats. And when I returned as consulting professor from Stanford back to Germany, we started immediately building UW1. UW1 was launched 2005, and it had as a topic telecommunication tests, in particular with respect to applying internet to space environments. Nevertheless, several other activities were started in other universities in parallel, and the second German CubeSat Compass 1 was launched in 2008 by the University of Applied Sciences in Aachen. And here the main objective was on technology demonstration, in particular magnetometer, magnetic coils, sun sensors in a combined way. In this year, we almost doubled the German population of CubeSats. So on 23rd of September, in parallel, UW2 the second satellite from Würzburg was launched. It continues with experiments related to internet in space. But in addition, we want to achieve also very advanced attitude determination techniques in the context of the small satellite frame. And from the Technical University of Berlin, in the same launch, BSAT was included, and they focused on the attitude actuators. So miniature reaction wheels, 3-axis stabilization of a satellite could achieve this way, were on board and are now actually tested in orbit. So you see, in Germany we had a lot of focus on technology demonstration, on advancing technologies for small satellites. And what was very helpful in the context was that we could initiate a national program on Pico satellites for educational purposes, which is headed by and funded in particular by DLR since 2007, and this pushed activities quite a lot. We initiated in Germany, in addition, an annual Pico nanosatellite conference, which first was national, but now became a European conference. This started in 2007, and every year we have alternating presentations in Würzburg and the year after in Berlin. Just beginning of October we had the last one in Würzburg, and there was an unanimous vote of participants that we will join forces to move towards very small satellite formations. So to combine different satellite activities, to standardize links, and to move towards application-oriented formation flying. Like in Japan, UNISEC, we are trying also to establish in Germany an organization of the different universities in order to further promote this Pico nanosatellite initiative. Finally, let me give some link into the greater context of Europe. The future activities in Europe are on one side headed by the ESA Educational Office. Activities like GENSO relate to establishing a network of ground stations. And here's an international cooperation between JAXA, NASA, ESA. So the related countries cooperate and support the universities to participate. Another European initiative is related to the Vega maiden flight, which hopefully in 2010 will occur, and it will carry 6 Pico satellites, and this combination is coordinated also by the ESA Educational Office. And finally, the most ambitious initiative is called QB50. That's an European initiative which was initiated this year, and the aim is to build 50 CubeSats to do in situ measurements of temporal and spatial variations of the lower atmosphere. So the altitude range between 90 and 300 kilometers, which is poorly accessed because lifetime is limited, but within the limited cost frame of Pico nanosatellite, it makes sense to go to such altitudes and perform the measurements. And finally, at the end of the lifetime, this offers the opportunities for additional studies about re-entry processes. So there are challenging initiatives on the way, and I think in Europe we are trying to progress in this way, and the universities are very enthusiastic. Thank you.
Thank you. So next speaker is Professor Hyo-Chon Ban. He's a director of space exploration engineering in KAIST, Korea. So please.
Thank you, Rei-san. Very nice introduction. Good afternoon, everybody. It's my great honor to join this plenary event and University NanoSat activity. In Korea, we have about 15 universities with aerospace engineering program nationwide. And then out of about 15 universities, we have 3 or 4 universities which are actively involved with Nano and Pico satellite programs. The universities are Korea Aerospace University and Seoul National University and KAIST. Unfortunately, we have never launched the CubeSat in space. So we have only one launch attempt for CubeSat by Korea Aerospace University in year 2006 with the Russian launch vehicle, which is the Dnepr, and obviously there was launch failure, so unfortunately CubeSat was not able to be placed in the orbit. And then at this point there's no launch plan, a near-term launch plan is scheduled in the future. So Korea is a little bit latecomer in this nanosat and CubeSat activity. So I would like to share with you some of the difficulties and problems we are facing as a latecomer in this activity. Okay, I'd like to show some of the videos, slides, which show some activities of each university for CubeSat and NanoSat activity. This is house set by Korea Aerospace University, led by Professor Young-Gun Jang, and who is really a pioneer and the leader in this particular area. I would like to give him a lot of credit for his excellent work to make house set 1 and try to launch the CubeSat into the orbit in 2006. And as I mentioned already, there was a launch failure in the Dnepr Russian launch vehicle, unfortunately, so that the CubeSat was not able to be in the orbit. So this is the only attempt and the very first attempt made by any Korean universities so far as far as CubeSat and NanoSat development is concerned. And these teams, Professor Young-Gun Jang's team, are working on a larger size, which is about 20 kilogram size NanoSat development program right now. So we'll see in the near future this team will make a really success in their launching of CubeSat in space. Okay, this is another CubeSat activity, but this is not the space grade CubeSat. This is a cancer activity with the SATRAC, which is Satellite Research Center, located in KAIST. And SATRAC has been involved with the micro-sat development activity. They have been extremely successful, launching 4 micro-satellites with great success already. So they have been working with Korea Science Academy High School, which is gifted talent school. So they have been working collaborating with the high school student to lead this CubeSat cancer activity. And this is Seoul National University activity for cancer led by Professor Jung In-seok. That team has been participating in this activity on an annual basis. And this is a team that I've been leading now. We are working on the CubeSat model development with the graduate student and undergraduate student right now. As I presented already, we do not have any Korea CubeSat launch the history at this moment, but with the great recent success in our national space program, I'm very much positive we'll be jumping into this worldwide trend, and then we'll make a successful launch that will take place in the next few years. That's my best judgment. Thank you for your attention.
Thank you very much. The next speaker is Mr. Freddy Pranajaya, and he's joined the Space Flight Laboratory at the University of Toronto Institute of Aerospace Studies in 2001, and he's a leader of the Advanced Systems Group at the Space Flight Laboratory. So, please.
Thank you, Ray. Today, thank you very much, first of all, for the opportunity to give a short talk on this subject. I would like to first go over the activities that we have in Canada, not necessarily only supporting our own missions, but also things that we are doing for our international partners and collaborators. At this time, the Space Flight Laboratory at the University of Toronto, we have 3 operational missions. One is, the first one is MOST, which is a 53 kilogram, more of a microsatellite class space telescope, which we built in 2003, and it has continued to operate since. In addition to that, we have 2 nanosats, the CanX-2, which is intended for demonstrating new technologies, but at the same time to perform some atmospheric science studies, sponsored by our own government. And in addition to that, we have the third one, which is NTS, which we built for a commercial venue, Comdev Limited, that is to perform ship tracking. This one, we believe, is actually one of the first, if not the first, nanosat or any satellite that actually is able to provide ship tracking data from space. In addition to all of those three, we actually have 6 new nanosatellites under construction, plus 2 additional ones under review for funding, for a total of 8 that will be coming in the next 3 or 4 years. The first one being an IAC2009, also a ship tracking nanosat, and that we are building for Norwegian Defense Research. Following that, we have a constellation of 4 nanosats, 2 of which are funded by our Austrian partner. It's called the Bright constellation. Those 2, the first 2 will be completed for launch in 2011, and with the additional 2, we're awaiting for a decision for our government to be deployed into a different orbit, so as to achieve a better star coverage. This is actually perhaps one of the instances whereby a nanosat is actually doing something, a brand new science that is perhaps due to other reasons or one or the other. It's probably more difficult to implement in large satellite, and yet we can do it on a small nanosat. Following that, we have the CANX 4 and CANX 5, a twin satellite mission. We are building for our own government to perform formation flying test. Is slated also for launch in 2011. And following that, our 6th satellite is actually a brand new satellite called NEMO AM. AM stands for Aerosol Monitoring. This is a mission that we have recently signed with our collaborators in India, the Indian Space Research Organization, to perform atmospheric studies, in particular to do aerosol monitoring in India in particular, but also around the globe. This also shows some promise, again, to provide new data sets to the overall space community, but in doing so, using nanosats. And last but not least, but it's not really a nanosat, it's actually a microsat. We are providing avionics for an M3M sat ship tracking satellite. Oh, sorry. From where we are right now, we've seen that the state of a nanosat of having a very high performance computer system, reaction wheel, propulsion system, and in addition, we are also implementing a redundant architecture on our nanosat so as to improve its own fault tolerance. We've been able to turn around a fast mission in less than 6 months from conception, from contract signing to delivery to the launch site, with launch on month 7th, very soon after that. In addition, we've maintaining our own network of ground stations. We started with 3 stations across North America and Europe, beginning in 2003, and now we have the capability to quickly deploy new additional stations, which we have recently demonstrated earlier this year. Basically pulling a 9-meter dish into our network within 2 days time frame, and basically continuing with the full command and data linking through our control center in Toronto. We have seen improved performance. We have nanosat that's actually breaking the megabit per second downlink limits, and we're continuing to push that to beyond 2 or 4 megabit per second. We are flying nanosats with extended Kalman filter to achieve full 3D control with up to 1 degree pointing accuracy with just sun sensors, but we are able to achieve 1 arc seconds, or we are targeting a performance of 1 arc seconds when we put the star tracker in the loop. The feature, the way we see it, it's always been the challenge to how to generate new data sets from a nanosatellite. Not necessarily recreating what's been done or miniaturizing everything. That in itself is already an achievement, but it would be much, I think, nicer if we can actually provide a data that is brand new, and which we are trying to demonstrate with some of our new and upcoming missions. But the key, I believe, is always innovation. So always to challenge yourself, and in doing so, always think about new things to improve components, materials, instrumentation, and all that. And perform collaboration that would foster innovation and creativity. Thank you very much.
And last speaker is Professor Sir Martin Sweeting. He's founding chairperson of SSTL in England. And he's a pioneer the development of small economical satellites for commercial, scientific, and military applications. And please, Sir Martin, make some comments. You don't have to come here. Just.
Arigato. Thank you, Ray-san. And if you forgive me from sitting and talking, and then I can just, I've made some comments and notes during the presentations by our speakers. First of all, I would just like to step back now 30 years and look at the, very generally, the development of small satellites and how that now perhaps is giving us some indication as to how the CubeSat and Nano satellite activities might develop. In my own field, in Surrey University, we started building the first, what were then 50 to 60 kilo microsats in 1979. In fact, it's terrible. It's actually 30 years ago, 1 month ago, that we started this project. And these 50 kilo satellites were the miniature satellites of the 1980s. And at that time, by the established space community, these microsatellites were considered a pretty wild and generally rather useless idea. And so in the very early days of our satellites, the first two USAT 1 and 2 satellites, they were primarily experimental, carried out technology demonstrations, some very limited space science, and a lot of training, and also schools education and inspiration for young people. In fact, there were some 1,500 schools that were interacting with the second USAT 2 satellite in 1985 to 87. But what was interesting is that the university at Surrey found, of course, that the cost of building and operating these satellites from university funds alone was unsustainable. And so after the first two satellites in 1985, we were faced with either stopping or finding some way to continue to support the project. And so in 1985, the university formed a commercial company, now SSTL, whose objective at that point was to raise an income stream to provide sustainable support for future microsatellites. But actually, in the 1990s, as these satellites developed, the microsatellites still had very limited utility. And again, we're seeing a parallel here with the CubeSat development over the last 10 years as well. So in the 1990s, the microsatellites had a very limited utility. And so again, they were primarily training projects, specifically with emerging space nations, and a very valuable one. But the established space industry still viewed them, even 10 years after their first emergence, as interesting but of no real utility. I think we should also recognize that AMSAT, the Amateur Satellite Service and Corporation, had also been developing these small satellites for communications and demonstrating their value in a particular niche area. But I think if we look at the current decade, round about the year 2000, the advances in microelectronics really suddenly allowed microsatellites to achieve real utility and to enter the commercial sort of space highway alongside the larger brethren. And subsequently, we've seen in the last 8 or 9 years, class of satellites in the 100 to 150 kilos and a little bit above, these small satellites providing real operational Earth observation services and generating new businesses. So what about the next generation of nano satellites? Well, 10 years ago, we launched the 6 kilo SNAP-1 satellite from Surrey in the year 2000. And that was built by students and staff and achieved a 10-to-1 reduction in mass, but also had all the capabilities of a typical 60 kilo satellite. And very soon we saw the CubeSats following on a similar scale, primarily educational focus. But their limited size really limited their utility to small niche applications simply because of the limited aperture for physical instruments. But again, we're seeing advances in miniaturization, new techniques such as swarms of these nanosatellites, which now may be able to operate cooperatively in orbit and provide very novel solutions to some new business and other applications. So maybe what we see now is CubeSats following the same trajectory. starting out primarily as educational, then as innovative ideas and technology come together, we start to see that these small, very tiny nanosatellites will start to generate new business opportunities, such as GNSS reflectometry. And because of the very large community that's grown up in CubeSats around the world, there are lots of people with innovative ideas. And so I think we will see these developing. And CubeSats still have a very important educational role, because in training young engineers, specifically with practical experience, as opposed to just simply computer simulations, and not only in the technology, but also in total systems engineering and also in management teams. Now, the same obstacles remain for CubeSats, and that is locating suitably priced launches, getting suitable space policies, and also the regulation that surrounds both the launching and operation of frequencies on spacecraft. But what I think is very encouraging is that governments are beginning to see that actually these nanosatellites have a major contribution to skills development and are also beginning to provide means whereby we can have some novel business opportunities. And so governments around the world, I notice, are beginning to address some of these problems. And I hope that we will see more launches and a more favorable policy environment to support the continuing growth of the nanosatellites. Arigato.
Thank you very much. So now is a discussion time. We have 25 minutes more. So the first, we are going to have three key questions, and then we have no time, so let's start. Question 1. Can nanosatellite give an impact on space technology? If yes, in what way? In this panel session, I'm not going to ask anybody, so just raise your hand and try to answer. Very good one. Okay.
I think, sure, nanosatellites will give us impact. And I think, in particular, universities, we are devoted to two avenues. First one is education. Second one is innovation and research. So with respect to education, I think we train young students to have a system view on micro-level implementation. And this will, I think, spread out in space technology as an overall area. System technology on one side and micro components to be integrated also on future large satellites. The other issue, innovation. Yeah, in universities we are trying to educate people in advanced technologies which are coming in the next 5 to 10 years. And here I think we addressed this already by combining capabilities of single limited small satellites into a formation, into a larger, more complex system. This will provide us new capabilities. And not so much has been realized in orbit so far. But small satellites offer big opportunities in this context to provide space systems of distributed satellites at a limited cost frame.
Thank you. Okay.
If I can add to what Klaus just said, the impact you can also see through the education of the future generation. But in that, what I mean is that you actually let these new engineers and these new future engineers actually continue to push the envelope of performance. As we've seen in our program, all of our young engineers or the students are actually being tested to generate something that's brand new, that's never been done before. So that would in my view would actually not only be beneficial for the future generation, but also energize the young minds, because they know they themselves are responsible in the development of some of this cutting-edge technology.
I think you have. Push the button.
I think one of the things that we've seen here in the in the United States, especially over the years, is the U.S. government really stepping in and seeing the benefit of CubeSats and small satellites. I've been at Cal Poly for way too long. I'm just having too much fun, but about 6 years ago, we were laughed out of the offices of of different U.S. government agencies, saying that CubeSats and student satellites are just toys. But I think just recently, over the last year and a half, you've seen the National Science Foundation really taking hold of CubeSats and really trying to promote space weather technologies. And you also have seen other U.S. government agencies purchasing 50 3U CubeSat buses to do science and technology in there as well. They don't necessarily know what experiments will go in there just yet, but they know that'll happen over the next few years.
Thank you. I just wanted to add one very quick comment on this particular question. Personally, I think that the very tiny nano satellites are likely to have an impact on space technology by providing a means to assemble very large apertures in space. If we look at the next generation of telescopes, we look at perhaps some other sensors in orbit, rather than launching very large-scale physical structures, we can either assemble them robotically from a series of small nano satellites, or we can have a sparse area arrays in a free-flying swarm and then synthesize the wavefronts from those in order to achieve a larger aperture without having to physically launch a very big satellite. And I think this may be one area specifically where these small satellites can have a dramatic impact on the way we approach space in the future.
Thank you very much. We'd like to take one good answer from audience, please. Yes. Microphone, please.
All right. Thank you for giving me the opportunity to answer that one. I think I really agree with what Sir Martin said as well. If you look at what can nanosatellites do in the future, of course it's what has been said before, to which I totally agree, having built an educational satellite, giving the students the opportunity to learn more than just from the book and be ready for industry much faster actually than before. But what you see on the application side, indeed, is that it offers a complete new view on low cost or multiple satellite applications that you can use in space. So I think it'll change the way that we look at, for instance, in-orbit spares or new constellations, as Sir Martin said, in the very near future, actually.
Thank you very much. So I think it's voting time. Please raise your hand if you think nanosatellite can give an impact on space technology. Please raise your hand if you think yes. Yes. Panelists too. Okay, thank you very much. So let's go to next question. Next one is quite tough. Are university nanosatellite projects sustainable? What would make it sustainable? So it's time for you.
Me? Yeah. Okay, a tough one for me. Thank you. Well, funding, of course, is a difficult problem. The launch, yes. Innovation, I think this is rather an easy one. And workforce development, yeah. I think this is a very important aspect of the nanosat activities in the universities. Radio frequency, yes. Debris issue, yes. Hurdle for newcomers. I don't know about this one. Okay, among these, let's see. For instance, okay, I'll pick up the space debris, okay?
Okay, sure.
Can you?
Yes.
A lot of people say that, oh, you're launching small ones and you're just leaving space debris in space. And this is not the correct way to defined. Well, this is, I don't go into the detail in this one, but I propose debris index. And this is the formula, very simple formula, which predict how many fragments one spacecraft, used spacecraft, would be able to produce within its lifetime in orbit. Can I have the next one, please? Sure. And here, the red portion is something what you can do to decrease the number. And basically, this debris index constituted from two components. One, explosion, and the other, the collision. The first one is for the collision. And if you make avoidance maneuver, if any of you have been here this morning, and avoidance maneuver can decrease the. And then. And the next one is the explosion. If you empty your residual propellant and everything, the energy dissipation, energy is expelled, then you have very small chance of explosion. And then the last one is the shorten the orbital life. So can I have the last one, please? And you have to be very careful to determine those parameters. But when this is my rough, very rough estimation. In case of the iridium or regular-sized sun-synchronous bodies, then the debris index will be something around 260. This will be a number of probable pieces of debris created in 25 years of its life. For smaller ones of 1 kilogram, it goes to 0.001. That means it has very little chance of creating other debris. So that means, well, this is not very much authorized in the space debris community yet, but this is something I proposed at the IADC last year this year in Bremen. And I think this gives you some idea that small satellite, I don't say harmless, but gives less and less harm, very much small hazard to other space bodies than compared to other bigger ones.
Thank you. So I'd like to invite a newcomer.
In fact, I was about to talk about technology innovation. As for the sustainability of NanoSat and CubeSat program, I'd like to discuss very critical and very important, obviously. But I would like to say technology innovation is probably the key factor in determining sustainability in the future. In fact, we have seen technology innovation already for the last 10 years. There has been tremendous progress and advance and innovation in CubeSat technology already. So if we have a huge breakthrough and innovation in using CubeSat NanoSat program, there will be not much worry about bringing funding and government support. So I'm very positive and optimistic that CubeSat program will be sustainable with technology innovation in the future, which will solve many problems, and then will be leading to great success in this program. Thank you.
Thank you. Professor Sweeting.
Thank you. I think that the answer is relatively straightforward, that to make it sustainable, you need to have money. Money then actually solves everything else, as with most things in the world. So if you have money, you can then buy the launches at a more expensive price, and they are available at a more expensive price. So if you have the money, you can buy the launches. And you can also pay to overcome the policy restrictions of licensing, which is, again, primarily a cost on small teams. And in order to get money, there are really two solutions, other than just robbing a bank. And that is to get government funding, because governments see the utility of these satellites in training and other applications, or they have business utility. And this is what we've seen in the trajectory of microsatellites, if we like. So I agree with my colleague that if we can have some innovations in technology and application which start to generate commercial revenues, then the system will become sustainable. Or governments need to have a significant funding line which allows universities to be able to procure launches, to be able to fill in the necessary regulatory hurdles, and also to operate the satellites on a continuing basis.
Thank you. Professor Schillings?
Yeah, I fully agree, but I want to focus maybe a bit more on the university perspective. I think not every university should go to be entrepreneurial, but in a university we want to train students, and launches, all the tests cost a lot of money. Nevertheless, I think it's very valuable to train students on real hardware. That's very important for the education process. But this cannot be afforded by, today at least, by the universities themselves. We need support from outside, from government agencies mainly, to keep this useful program alive. I think we are now in a critical phase, because in the first years a lot of enthusiasm of student of faculty entered, and this helped to bridge some of the difficulties. But now first satellites are in orbit, most first experiments are done in orbit, and so the enthusiasm is hard to maintain. So we need to go to a continuous operations, and I think not everywhere we have achieved this. Yeah, so in some places, like in Canada, like in the UK, you went into the production, but it's difficult. I think we have not for every university such a facility to go to the market. So nevertheless, we need the government support. Otherwise, I think it will have some kind of collapse.
Okay. Do you want to make some comment? Okay. Okay. Roland first. Okay.
And I think one of the challenges, especially for the smaller, not as known schools, it's very difficult to have your program go on. And I think what we found with our first Russian launch is, we waited about 2 years, 2-year delay before it was launched. The launch was did not make it to orbit, and there was a few universities in the U.S. that basically closed up shop after that failure, because the funding stream that they got was from the universities and private donations. And after the rocket went in the ground, there was nothing to show for it, and so the funding dried up. And I think one of the questions is, how do we get more universities to participate, and a lot of the smaller universities in particular?
If I could just pick up on that, I agree with you. I think I've seen one statistic, and I can't quote it exactly, but I think there are roughly 10 times as many nano satellites on the ground as there are in orbit. And that leads us very closely to the problem of affordable launches. And even if we can get the enthusiasm of the staff and the students, and actually generally my feeling is that the student enthusiasm does continue. The staff get a bit tired, but the students year by year still maintain their enthusiasm. You need still green money to buy launches. And that is as big as the actual cost of the components of the satellite. So this real tangible money and the access to regular and affordable launches is really key. And as I say, there's this big mountain of nano satellites on the ground which we need to get into orbit. So government funding at this stage is absolutely critical to help do that. And I know that some governments are taking initiatives to provide the launch capability for universities or to provide some funding.
Thank you. Do you want to make some comments? I want to get an answer from audience. Is it okay? So, your time. Is there anybody to have good answer?
In my opinion, I think there is a demarcation here between making these projects sustainable in developed countries and in developing countries. While the universities in the US or Canada or UK can afford such programs and gives such amount of funding to the small satellite groups, in developing countries like in India, it is very difficult to get that kind of funding and sponsorship on a student project. And as one of you rightly said, these projects, since they are in the beginning, they are still looked upon as they are toys. And so in my opinion, in developing countries, to make these projects and these university projects sustainable, the initiative should be taken by the respective national space agencies, and they should come forward and support groups in terms of helping them procure components or getting them test facilities and such other facilities, so that we can better integrate these small satellite projects in various universities, and maybe form a sort of a small consortium of such projects and keep giving them technical guidance as well as guidance in terms of funding and procurement of components. Thank you.
Thank you. Is there anybody who want to answer? Or make a comment? Okay, sure.
No, I think it's important to move towards internationalization. And I think that's the last point of our discussion. We come into more detail. What I would suggest to you is maybe if own governments are reacting slowly, you can nevertheless participate because there are international scholarships available. For example, in my university, we have the so-called Space Master program together with 6 other partners throughout Europe. And the European Union provides 25 scholarships for developing country students to participate in such a program. And after having gone through such programs, you can return and can influence in your home country. You can introduce the knowledge you bring with you back home and build own activities up in your own country.
Okay, thank you. So quick voting. Do you think university nanosatellite projects are sustainable? Raise your hand if you think yes. Oh, most of you do not think it's sustainable? No? Once again, do you think university nanosatellite projects are sustainable? Please raise your hand if you think yes. Thank you. Thank you.
How about those that think not?
Oh.
If they raise their hands, it would be interesting to see.
Okay, all right, okay. So, if you think it is not possible, it is not sustainable, please raise your hand. Not. Negative. Oh, good.
Both equal.
Okay, thank you. Okay, so very unfortunately, we do not have enough time. So the last question is just if we have 2 minutes left. So if one or 2 comments to this question. Okay, go ahead.
As you can see from my earlier slides, we do have a lot of collaboration with our international partners. It is true that we do receive a lot of support from our own government, our agency, our defense department, and also our federal and provincial governments. However, we do also enjoy a very good collaboration with our other international partners. So to that effect, I would say collaboration, yes, that would be very beneficial. However, I think it's also important to emphasize that it has to be collaboration that fosters creativity, because creativity and innovation will eventually lead to sustainability of the entire program.
Perhaps if I can add to that while our chairperson is busy, I think there's a very good opportunity for collaboration in ground station networks. So by using, to some degree, common ground station standards, having individual groups providing ground station networking is very important and very useful. Likewise, conferences, to a lesser extent, trying to bring together to aggregate launch opportunities, satellites, so that we can get more launch opportunities. Collaborative missions, I think, becomes more difficult, but would be very nice.
Thank you very much. We wish we could talk more, but we have no time left. So one comment from Professor Nakasuka.
So I think, I'd like to propose one international collaboration to these questions. So I think, as you know, the most educational satellite uses amateur frequency, and as you know, the amateur frequency is very, very congested, and it's very difficult to assign the frequency to the many satellites. So I think we need to think about some more effective usage of the very limited frequency resource. And so I think we'd like to think, we should think about such kind of the new technology of CDMA, of the usage of the very small amount of the frequency resource. How do you think about that? I think it requires a little technological innovation in order to make it very small, but the CDMA technology is very popular in the mobile phone, and so I think it's possible to apply that to the satellite. Okay, so this is my comment.
Thank you very much. So let's give all of us a big hand. Thank you very much for participation. I really appreciate that.